Hi and welcome. I am trying to learn particle physics today, antimatter, and after we've done it, we're gonna do a bit standing yoga. And if you participate in the standing yoga, then it's relatively obvious. The most basic definition of an antimatter particle is that it is the same as matter particle, except that it has the opposite charge. So the familiar electron, for example, with a negative charge of -1, has an antimatter equivalent called a positron that has a charge of +1. Let's go back to something. We had here, to find out if the weak interaction was differently in but parity symmetry was broken with a weak interaction, had huge ramifications for explaining how the weak force worked and provided a first window on other broken symmetries within what became the standard model, including the CP symmetry violation that might explain why matter dominates over antimatter in the universe. So there's more matter than antimatter. We read somewhere 2/3. 2/3 is matter and 1/3 is antimatter. I didn't know the right way around. Okay, there's something with CP violation that could be an explanation why there's more matter than antimatter. No, and in the most basic sense it is that the electron has same thing against it, just that it has the different charge, so it is a positron. Similarly, an up quark charge plus 2/3 is partnered by an up anti-quark charge minus 2/3. The same goes for composite particles made up of quarks. They too have the exact mirror equivalent. For the proton, quark combinations up-down charge 2/3, 2/3 plus minus 1/3 equals 1. There's the antiproton quark composition anti-up, anti-down charge minus 2/3 plus minus 2/3 plus 1/3 equals -1. What it's saying is there are the protons, and these protons consist out of 3 different quarks. For example, an up and a down quark. So they then totally have every quark is 2/3 positive, 2/3 plus 2/3, but there's a down quark in it, so it has exactly 1. So 2/3 plus 2/3, 1.5, and now 1/3 comes away. Of the whole total, whatever, it makes 1, and the proton has a charge of +1. And an electron, no, and there's now the antiproton. The electron, had we already said, has its positron against it. The proton has its antiproton against it. It has a charge of -1, like an electron. So far so simple. But the complicating factor is that charge doesn't just mean the familiar, everyday electric charge. 3 fundamental forces are covered by the standard model: electromagnetism and the strong and weak nuclear forces. Each of these forces has a charge associated with it, and antimatter particles have opposite values for these charges too. Opposite values. Not every particle has an antimatter equivalent. Let's see it again. What was here? It was more matter than antimatter. Not every particle has an antimatter equivalent either. Bosons, these are the particles that transmit influences within the standard model, tend to be their own antiparticles. What if the bosons are the true neutrons of the universe? No, bosons have no antimatter equivalent. And it could be because they are themselves their own antiparticle. These include photons and the mass-giving Higgs boson. They also don't have an antimatter partner, and also the Higgs knot. To date, no one has been able to establish whether neutrinos and their partner antineutrinos are different or the same thing. Okay, there are the neutrinos and they are sometimes emitted. I mean, they're emitted all the time, would you say. But it could be that the antineutrinos are the same as the neutrinos. So, The story of the discovery of antimatter is almost as remarkable as the fact of its existence. So we're saying how it was discovered, we have to pay just more time left, is extraordinary, but also that there is antimatter at all. What is that for concept that there is antimatter? In the late 20s, physicist Paul Dirac was it is still a violation of symmetry if not everyone, for example, the Higgs and the photons and the bosons have no antimatter partner. Even if it would explain why there is more matter than antimatter. In the late 20s, physicist Paul Dirac was looking to develop a theory that combined quantum mechanics with Albert Einstein's special relativity to explain how things both very small and very fast, in this case electrons, near the speed of light, behave. Okay, it was in the 1920s when physicist Paul Dirac was looking to develop a theory that combined quantum mechanics with Albert Einstein's special relativity to explain how things both very small and very fast, in this case electrons near the speed of light, behave. So he wanted to know how electrons behave when we got to the speed of light. The equation Paul Dirac developed had two solutions, corresponding to an electron in each of its two own states of quantum mechanical spin. Okay, but it also had two other solutions corresponding to electrons with seemingly negative energy, or alternatively with opposite positive charge. Okay, made an equation, and 4 results were correct. Let's continue. At first, Paul Dirac ignored the finding out of what he would later call pure cowardice. I think what you mean. Nah, I don't know what I want to say. I haven't thought it through if it's what I want to say. It was only 4 years later, in 1932, that US experimentalist Carl Anderson found something acting exactly like a positively charged electron in cosmic rays. So then in the year 1932, there was someone else, his name was Carl Anderson, and he saw that electrons behaving exactly the same way as if they were positively charged in cosmic rays. They're just somewhere in the sky or whatever. The discovery of the positron marked not only the first antimatter particle, but the first time something never before seen in nature was predicted first. So they predicted something which we had not seen. That is postulated to exist based on theoretical rather than experimental evidence. And that is what theoretical physicists do. Think about stuff, and when they're having the idea there has to be somewhere a positive electron. And now they have predicted it. What is what to do? And when they come to experimentalists, they have to prove that it is there. Dirac's discovery was guided purely by the human imagination and the power of mathematics. Antimatter exists in our world too, and not just in cosmic rays. You just have to be very alert to spot it. Everyday antimatter generally takes the form of positrons produced in radioactive beta decays. Okay, the beta decay is doing positrons. They lead transient lives before annihilating with the first electron they encounter, producing energy as gamma rays. Oh, that is very interesting. I want to take it as simple as it's written here, as if it would be true. Maybe it is true. There's beta decay reckoning. There are neutrons, they're splitting up, giving up positive proton and an electron, whatever. And now there's an electron wandering around in the sky, a positron, and sometime this positron gonna meet an electron, and as soon as it meets it, gamma ray is produced. I don't know if it's production of gamma ray, but it just is an energy event. It could be how gamma ray could be produced or something else. I think it's very interesting. Like the occasional breaking of the most delicate of winds, we all emit the occasional positron thanks largely to traces of radioactive potassium-40 in our tissues. Like the occasional breaking of the most delicate of winds, we all emit, so humans are emitting, positrons. And that is thanks largely to traces of radioactive potassium-40 in humans' tissue. Okay, humans have for some reason whatsoever potassium-40 in them, and that causes them, and because potassium-40 seems to be some type of radioactive thing, and that sometimes does beta decay and giving off a positron. And as soon as that hits the first electron in the room, it gives gamma rays. A medium-sized banana produces one maybe every 75 minutes. Medium size. A bag of Brazil nuts or a worktop or bedrock made of granite ups the ante considerably. So whatever, a banana or some nuts or some whatever worktop is and a block of granite are giving up a lot of electrons. And we can take it already, a banana is giving up one whatever it was, 1 positron per hour. None of this is a danger to us. You should. By saying it's the least now measurable big danger. The energy released by each annihilation amounts to precisely 2 electron masses or 0.022 mega electrovolts. Okay, if such a positron meets an electron, the amount of energy is 1 mega electrovolt. And in the standard units of very small energies, considerably less than 1 millionth of the energy of a flying mosquito. And that thing has the energy of 1 millionth of a mosquito. No, but is dangerousness completely measurable by its energy? Okay, we're saying it very early. Technologies designed to propel humanity further, such as antimatter drives or rockets, or to blow us to kingdom, come, such as antimatter bombs, aren't exactly immediate prospects either. Okay, we're saying there's some people working on building cars or rockets or big bombs out of antimatter, but that they come into existence, that we either drive around them peacefully or they're blowing ourselves to pieces, is not really realistic because the total energy of stable antimatter contained so far over decades of experiments isn't enough even to boil the water for a cup of tea. Because we're saying in all the experiments we had made together in the last 100 years, they haven't even enough energy together to make some water boiling. Although you would need a vessel a couple of 100 meters across to hold it in place. Because water is so big? Whatever, there are some dimensionary problems. So what is antimatter good for? We're having 2 minutes for you. That is one of the favorite questions of Tara Shears at CERN's Large Hadron Collider beauty experiment. There's someone saying, antimatter is really esoteric, isn't it? She says. Or was it a question? She says, you probably don't expect antimatter to help diagnose cancer or help with heart problems or have any practical benefit at all, but it does. So we're saying it does not help to diagnose cancer, it does not help with heart problems, and there's no other benefit, but there is maybe a benefit. Positrons make up the P in a PET scan, which stands for positron emission tomography. Here, the annihilation emissions of positrons in the radioactive tracer you swallow or someone can swallow can illuminate all sorts of potential internal nasty. I don't get it. More or less, there's no use, but it helps to understand the universe. And who knows, maybe someone finds an anti-emitter, and that is of use. And we can build cars which actually drive. No, I think that is enough. No time to make a joke. That was the antimatter part to particle physics. If you were here for particle physics, you can go directly to the next part of particle physics, where we're going to do the Paul Dirac thing there, and then reach the end again, maybe. If you're here for standing yoga, well, we're going to do a standing yoga. If you participate in this the arm desk, we're going to feet standing together, breathe in the arms up. Out the arms down. In and out. Out and down. In and out. Out, lean back, drop shoulder blades together. In and up. Out the arms down. In and up. Out to the side. In and up. Out to the other side. In and up. Out and down. Breathe in the arms up. Lean back, drop your shoulder blades together. In and up. Out and down. Now breathe in the arms up. Bring the hands to touch and roll the hands downwards. It wasn't even a minute, but I don't know if we can make 80 yoga flow in another minute right now. That was whatever you thought relaxing. I thank you very much in advance.